So you've probably heard the term surd before, but now we're going to call it a quadratic surd, and that is a number of the form square root a, and that a is any old number, and a must be a rational number but not a perfect square. Because if a is something like 25, square root of 25 is 5, which is not a surd, it's just a natural number. And generally when we say a surd of order n, that means we can have an nth root here. So when we do one like this, that's an implied, that's square root of a, but we don't put the 2 in because we know that it's just there. But if we wanted something like the cube root, so for example, the cube root of 8 is 2, because that's 2 times 2 is 4 times 2 is 8. So we could also have like a fourth root of 16. That's also 2, because if we go 2 times 2 times 2 times 2, we get 16. So we can call that an nth root or a surd of order n. So something like the square root of 81 on 4, that is not a surd, because this is the same as 9 on 2, so it's just a rational number. But if we had something like the square root of 37, that is a surd, because if I put that on my calculator, it goes forever. Something like the cube root of 15 is a surd of order 3. And we can say the cube root, and if that was a 4, it would be order 4, if it was a 5, it would be order 5, etc. So let's have a look at some properties of square roots. So if we have something like square root 3 times square root 5, oops, I just wrote the answer, that is square root of 15. So what we say in a general rule is the square root of a times the square root of b is the same as the square root of ab. We can also say the same with fractions. If we have the square root of 32 on 6, that's the same root of the square root of 32 on the square root of 6. By definition, we say the square root of a on b can be broken down into square root of the top over the square root of the bottom. All right, so what we're going to do now is we're going to practice writing surds in simplest form, and the way to do that is we have to look for a perfect square that goes into 72. So the first thing I'm going to do is list all my perfect squares, and my perfect squares are 1 times 1, which is 1, that's no use to me, 2 times 2, 3 times 3, 4 times 4, etc. I'll go to 144, that should be enough. So whenever you're going to do some sort of assessment, if you list your perfect squares down the side, that's the number that we're looking for that goes into 72. So the first I'm thinking 72 can be written as 36 times 2, or square root 36 times square root 2. Square root of 36 is 6. So that can be written in simplest form as 6 root 2. So square root 28, I can write that as 4 times 7, which is square root of 4 times square root of 7. In simplest form, 2 square root 7. Square root of 700 over 117. Now I'm being tested, aren't I? So 700's easy enough because it's going to be 100 times 7. And then I go and see which of these numbers goes into 117. And I'm thinking that is 9 and 13. So on the top I'll have 10 root 7, and on the bottom 3 root 13. And am I happy with that? Yep, they've just written a little different way. If you look in your book, they wrote it as 10 over 3 square root 7 over 13, but that's exactly the same thing, so I'm happy with my answer. So what do we have? A, B, this was C. So I'm going to do D underneath here. Square root 99. Well, I'm thinking 99 is 9 and 11. And I know the square root of 64 is just 8. So this is 3 square root 11 over 8. So if you like, at this stage now, if you want to go and have a go at these questions, you can now do question 1. You can do 2C question 1 now if you want to go and get started. And then the next example goes on to question 2. So if you want to stop the video, by all means do so. If not, let's keep going. We can add like surds. So it's a bit like algebra. So if we have 4 square root 3 plus 7 square root 3, I can write that as 11 square root 3. It'd just be like 4x plus 7x is 11x. And if I had 10 square root 5 minus square root 5, that would just be 10 minus 1, which would be 9 square root 5. So in terms of algebra, we can write that as m root p plus n root p equals m plus n, add those coefficients, root p. And if we minus them, m root p minus n root p, we get m minus n square root p. Look, I don't think we need rules for those. I think you can just look at it and kind of know what to do. How does it get a bit harder? Well, sometimes we're going to have to simplify first. So let's look at these ones here. I haven't got any like surds there. So what I'm going to do is break them down into like surds and then see what happens from there. So 147, of course that's 49 times 3, because remember I'm always looking for my perfect squares so that I can simplify them. And then 108, I can think that's 36 times 3. And 363 is 121 times 3. Takes a little while to think of those sometimes. The more you do it, the better you'll be. So it's 7 root 3 plus 6 root 3 minus 11 root 3. So 7 plus 6, 13. Take 11. My answer is 2 root 3. For B, I can't simplify the first ones. Root 3 plus root 5. 20 is 4 times 5. 27 is 9 times 3. 45, I'm thinking 9 and 5 for that one. And then minus 48 is going to be, that's going to be 16 and 3. So I'm going to get root 3 plus root 5 minus 2 root 5 plus 3 root 3 minus 5 root 3 minus 4 root 3. Like terms, root 3 plus 3 root 3 is 4 root 3. Take away 4 root 3 is nothing. And then I've got square root 5, take 2 square root 5 is minus square root 5. And I've made a boo-boo. Sorry, I'm not going to go back and fix this up, but I am going to tell you that this should have been minus 3 root 5. And then I've got root 5. I really mucked up this one. That's a plus. That's 3 root 5. We end up with 0. Sorry. I can't be bothered editing. You'll be right. Sorry, guys. But that's what happens with that one. So once we've done up to that point, if you go to the exercise, you can now do questions 2 and 3. And it's probably a good idea to do that now before we get on to the next bit, which is rationalising the denominator. So what do we mean by rationalising the denominator? Well, when I have something like 3 over root 5, to rationalise the denominator, it means that in my denominator, I don't want to have an irrational number. I want to have a rational number or a whole number. So the way I'm going to do that is I say, if I times this by root 5 over root 5, on the bottom I'll get square root 25, which is 5. So see how now all we've done is we've effectively times by 1. So we haven't changed the value, but we've been able to rationalise that denominator, make it not a surd anymore, but a integer. You don't always have to do that. Sometimes it's good to do it. I know it's come up in our trigonometry, so I've probably mentioned this a little bit. But let's have a go at some questions. So let's look at A. 1 on 2 root 7. Now the 2 is already rational, so I don't need to do anything with the 2. But I will multiply by root 7 over root 7. So I'm effectively multiplying by 1. So now on the top I'll have square root 7. And the bottom I'll have 2 times the square root of 49, which is just 7. So I get root 7 on 14. All right, so that's a little bit harder when we do one like B. That's a bit of a year 10 thing, the first one, but this is a bit more year 11. 1 on 2 minus root 3. Now we go back to old mate Dops that has reared its head a lot this year. Difference of perfect squares. If we have A minus B, A plus B, we get A squared minus B squared. So the middle term kind of disappears. So that's what we want to do when we look at this one here. So if I multiply this by 2 plus root 3 on 2 plus root 3, we're effectively multiplying by 1. But what's going to happen is when I have my plus and my minus, we're going to get rid of that middle term. So this will tell me on the top we're going to have 2 plus root 3. And on the bottom, I'm going to get A squared minus B squared. So I get 2 plus root 3 over 1, or just plain old 2 plus root 3. So we have a rational denominator. We've rationalised the denominator because now it is in fact 1. So I've put in an extra page here because I knew this would take a little bit. Let's have a look at C. It's 1 over root 3 minus root 6. Difference of perfect squares, so we times by root 3 plus root 6 over root 3 plus root 6. And we will use the same technique in complex numbers later on. And these sort of get called, there's this name, the conjugate. So the trick is make sure you don't change that first value, only change the sign of this second one because we want a difference of perfect squares. So this is all right. And on the top, we'll get root 3 plus root 6. And on the bottom, we'll get root 3 squared minus root 6 squared, or 3 minus 6. So root 3 plus root 6 on minus 3. And there's, I think the book they write it as minus 1/3 root 3 plus root 6. Same. And last one, let's have a look. We've got 3 plus root 8 on 3 minus root 8. Same technique, times by 3 plus root 8 over 3 plus root 8. So on the bottom, we're going to get 3 squared minus root 8 squared. And on the top, we're going to get 9 plus 3 root 8 plus 3 root 8 plus 8. So we get 17 plus 6 root 8 over 1. I'm not going to bother writing over 1. 17 plus 6 root 8. Then you look up the back of the book and you go, oh, damn it, it's different. You know why? Because we can write this as 17 plus 6, and we can write 8 as 4 times 2. So then this becomes 17 plus 6 times square root 4, 2 times root 2. So the simplified answer is 17 plus 12 root 2. So just watch for that. If your answer doesn't match, you might just have to go through and simplify it. And our last one, example 9, expand the brackets in each of the following and collect like terms. Express your answer, simplest form. All right, so we've got 3 minus root 2 squared. Better just to write it out. And if anyone writes that's 9 minus 4, straight to nerd jail for you. Because we have to go 3 times 3 is 9 minus 3 times root 2. And then we'll do minus 3 root 2 plus 2. Minus times a minus is a plus, so we get 11 minus 6 root 2. And then this one I'm going to write out 3 minus root 2, 1 plus root 2, 3 times 1, 3 times root 2. The bracket. Then I'm going to do root 2 minus root 2 times 1 and minus root 2 times minus root 2. So I'm going to get minus root 2 minus 4. 3 take 4 is minus 1. 3 take 1 minus 1 minus 2 root 2. Silly me. Sorry, I did that a bit wrong, didn't I? Root 2 times root 2 is root 4, which is 2. So 3 minus 2 is 1, and then 3 minus 1 is plus 2. That's bad, isn't it? Don't you do that. So that's equals 1 plus root 2. One plus 2 root 2. You just got to be careful, don't you, with your signs, otherwise you'll muck it up, and that's a good example of how you can muck it up. All right, so that's the end of 2C. There's lots in exercise 2C, so I'll give you a couple lessons to do that. And I will get on to 2D next time.